Hi everyone, and welcome back to the good stuff that we have been doing. Today in this video we're going to try to evaluate this beautiful integral over here, and it says this is the integral from 0 to pi of tan inverse of 1 plus cosine of x dx, and the answer is actually pi times cotangent inverse of square root of phi. And this integral, we did it already. It was a very 35-minute video long where we use the fact that 1 plus cosine of x is 2 times cosine squared of x over 2, and for that reason this integral became 0 to pi of tan inverse of 2 cosine squared of x over 2 dx. And then this is, I think this is going to be twice the integral from 0 to pi over 2 of tan inverse of 2 cosine squared x, and we turn this into the integral from 0 to pi over 2 times the integral from 0 to 2 of cosine squared x all divided by 1 plus t squared cosine to the fourth power of x dt dx. So that was a very long video, and if you are interested in this solution, please go to the video and enjoy yourself. It's already posted on this channel. On the other hand, today for this video we're going to try to evaluate this integral using the complex number method, whereby we're not going to use this is the double integral method, because here you can see two integrals appearing. But today we're going to just use the fact that the logarithm of a plus bi is equals to the logarithm of the square root of a squared plus b squared, which is the modulus of a and b, plus I times the tan inverse of what? B over A. Okay, we're going to use this very nice formula, as we shall soon see. So basically we're going to write the integral from 0 to pi of the tan inverse of 1 plus cosine of x dx. So notice that the tan inverse, notice that in this setup here, if we take, say, a to be 1, so the logarithm of 1 plus bi is equals to the logarithm of square root of a squared plus 1 plus I times the tan inverse of b. So basically the tan inverse of b is the imaginary part of this. This is the real part and this is the imaginary part. So this basically, this is the integral from 0 to pi times the imaginary part of what? Of logarithm of 1 plus I times 1 plus cosine of x dx. So basically the imaginary part of this logarithm expression is actually equals to tan inverse of 1 plus cos x, and we're going to use this fact to solve this integral. So what to do next, I'm going to take this out. So this is the imaginary part of the integral from 0 to pi of what? The logarithm of what? 1 plus I times cosine of x. And if you follow this channel, you will notice that earlier today, some few hours ago, I did a video where we explained that the integral from 0 to pi of the logarithm of a plus bi, no, not a plus bi rather, I think it's it's a plus b cos x, yes, of the integral of a plus b cos x. So this, I established this result on this page. He said this is equals to pi times the logarithm of what? A plus square root of a squared minus b squared all divided by 2. So pi times all of this. So this integral, so in this case we're going to take a to be 1 plus I, and then we're going to take b to be just I. So essentially you will see that this integral, this will be the imaginary part of what? Pi times what? Times the logarithm of what? 1 plus I, then plus square root of 1 plus I squared minus I squared all divided by 2. Notice that the logarithm of a over b is same thing as log a minus log b. So essentially we could write this as, and notice that I squared is -1, and also 1 plus I to the second power is 1 plus 2i minus 1, which is essentially going to be 2i. So this is the imaginary part of the, this is pi times the imaginary part of the logarithm of 1 plus I plus the square root of what? This will be 1 plus, this will be just 2i, because 1 plus I squared is basically 2i. So this is going to be 2i, then then this is minus negative 1, which is plus 1, so 2i plus 1. Then I'm going to subtract it by pi times the imaginary part of log 2, but the imaginary part of log 2 is basically 0. So we discard this away because we need the imaginary part of the whole expression. So the imaginary part of this is purely real number. Pi log 2 is a pure real number, so we discard it. So basically we're looking for pi times the imaginary part of the logarithm. Then you have a 1 plus I plus the square root of what? 1 plus 2i. Now we're going to use the representation of complex numbers, because you know that for complex number a plus b, you could write this as the modulus of this, which is a plus bi. The modulus is a square plus b square times e to the I theta, where theta will be tan inverse of b over a. Okay, theta will be the angle between these complex numbers. So basically we're going to write this part as pi times the imaginary part of the logarithm. Now 1 plus I, the modulus for 1 plus I is basically square root of 2. So this will be square root of 2 times e to the I times tan inverse of 1, which is pi over 4, e to the I pi over 4 plus, now this will be a square root, so we have a square root term, but essentially this will be the modulus will be 1 plus 2 squared, which is square root of 5. So you have a square root of 5 times e to the what? The argument is 2 over 1, that is tan inverse of 2, so e to the I tan inverse of 2. Okay, then this would be equal to pi times the imaginary part of the logarithm of what? So you have a square root of 2 e to the I pi over 4, then plus this will be the fourth root of 5 times e to the I 1 over 2 tan inverse of 2. Okay, so next, what happens next that we are going to continue, we're going to write this as pi times the imaginary part of the logarithm of, here you have a square root 2, so you can this is square root of 2 times what? Cosine of pi over 4, yeah, then plus the fourth root of 5, that is cosine of 1 over 2 tan inverse of 2. Okay, plus I times square root of 2 sine of pi over 4 rather, plus sine of 1 over 2 tan inverse of 2. Again, the imaginary part, we know that the imaginary part of logarithm of a plus bi is tan inverse of b over a. So essentially this whole expression is pi times the tan inverse of b over a. This is the b part. So we have a square root of 2 times sine pi over 4 is basically 1. So you have a 1 plus, so here you have a sine of 1 over 2 tan inverse of 2, and divided by, so you have a 1 plus okay, I even forgot the fourth root of 5 here. I forgot the fourth root of 5 here. So let me write that one down. So you have a fourth root of 5 times sine of what? 1 over 2 tan inverse of 2 divided by fourth root of 5 times the cosine of 1 over 2 tan inverse of 2. Okay, now let's simplify this inner term. Okay, how do we simplify the sine of 1 over 2 tan inverse of 2? Well, let's say we have a sine of 1 over 2 times the tan inverse of 2. how do we go about this? Well, let t be 1 over 2 tan inverse of 2. Okay, let me do this by the side rather. I think that one is better so that I will not disrupt the flow of the work. Okay. So let's set t to be 1 over 2 times the tan inverse of 2. Then how do we are looking for sine t and then cos t. But if t is 1 over 2 tan inverse of 2, that basically means that 2t would be tan inverse of 2, which means that 2 would be tan of 2t. So tan of 2t will be 2, which means that there will be a triangle here where we can call here as 2t, and then we can call here as 2 and label here as 1. So here would be square root of 5. So basically here sine of 2t would be 2 over square root of 5, and then cosine of 2t would be 1 over square root of 5. So we have sine of 2t and cosine of tt, but we need sine t and cosine t. So we know that 2 cosine squared t is 1 plus cosine t. So essentially cosine of t is square root of 1 plus cosine of t all divided by 2. So that would equal that would actually be equal to square root of 1 plus 1 over square root of 5 all divided by 2, and which is square root of 1 plus square root of 5 all divided by 2 square root of 5, and that would be 1 over 4th root of 5 times square root of 1 plus square root of 5 all divided by 2. Okay, so now we have the value for cosine of 2 cosine of t. How do we find sine of t? Well, that one should not be too hard for us because we know that also 2 sine squared t is 1 minus cosine t all divided by 2, which means that no, we don't divide by 2. No, we don't divide by 2. So we just leave this is 1 minus cosine of t. So 2 sine squared t is 1 minus cosine of t, which essentially means that sine t is square root of 1 minus cosine t over 2, which we could write at 1 over 4th root of 5 times the integral from the integral of you would have, how do we do this, 1 minus 1 over square root of 5 all divided by 2, right? Yeah. No. I think I rushed this thing too much. Yeah, I rushed it a bit. So this will be just square root of 1 minus square root of 5 all divided by 2, which is basically square root of 5 minus 1 over 2 square root of 5, and that would be the 4th root of 1 over, this is what I want to do, 1 over 4th root of 5 times what? Times square root of 5 minus 1 all divided by 2. If you multiply the top and bottom by square root of 5 plus minus plus 1, you will get this as 1 over 4th root of 5 times what? 2 divided by 1 plus square root of 5. Yeah. So you have the values of sine t and cosine t. Okay. So this is, if we're going to go back to our work, let's briefly explain where we are. So we simplified up to this level, and then the next thing on our sleeve is for us to get the values of the sine and the cosine. We already find the sine. We say this is pi times the tan inverse of, now we have a 1 plus, this is the 4th root of 5 multiplied by, the sine gave us 1 divided by the 4th root of 5 multiplied by what? I think we have a square root of 2 divided by 1 plus square root of 5. Yeah. Then the cosine gave us, this is 1 plus, you have 4th root of 5 times 1 divided by 4th root of 5. So you have a square root of 1 plus square root of 5 all divided by 2. So this 1 plus square root of 5 over 2, let's call it t. Okay. let's just donate it by t. Let t be the whole of this expression. So this will be pi times the tan inverse of 1 plus, this cancel out already, so we have 1 plus 1 over t divided by 1 plus t, because already this cancel out, so we have a 1 plus t. So notice that this will be t plus 1 all divided by, this will be t plus 1 over t all divided by 1 plus t, and that will just basically be 1 over t. So this is essentially going to equal pi times the tan inverse of what? 1 divided by square root of 1 plus 5 all divided by 2. And this is the golden ratio. The golden ratio phi is 1 plus square root of 5 all divided by 2. So we're going to write this as pi times the tan inverse of 1 divided by the square root of phi, which is pi times the cotangent inverse of square root of phi. Now you can see that we have achieved what we came here to do. We claimed at the beginning that this integral is equals to pi times cotangent inverse of square root of phi, and we have tried to keep our word and lived up to the task. So that is that for you. So thank you very much for watching this video today, and please do subscribe to the channel. Bye, and thank you very much.